All right, here we go. Problem 14. We've got a point and we've got a plane, and we have point Q such that P and Q are equidistant from pi and PQ is perpendicular to pi. Oh, that's cute. Okay, so just to help you visualize it, we've got a plane at some angle. We've got a point P that is probably not in the plane. We can double check that if you substitute it in. Yeah, it's definitely not in the plane. And I'm just going to put it above the plane just for visualization's sake. And then point Q is equidistant from pi. And so that might be hard to visualize. It could be in an infinite number of places, but then it says the line PQ is perpendicular to pi. And so what that means is I have to go along the normal vector. So this is perpendicular to the point to the plane pi. And so that tells me exactly where point Q needs to be then. Point Q needs to be on the other side of the plane. Otherwise, you can't be equidistant. So point Q will be somewhere over there on the other side of the plane. And so really all I need to do is just travel along the normal vector. And so let's try to find the normal vector of the plane and travel along it from the point to the plane and then one more time. So let's see how that works. So the normal vector to the plane is 4, -3, and 1. You can just read that from the Cartesian equation there. And then the line PQ can be described as the point P plus a parameter times the normal vector. What I'm going to do next is parameterize that, saying that the x points along the line PQ are y equals 1 plus 4t, x equals 1 plus 4t, y equals 0 minus 3t, z equals 2 plus t. And then I'm going to substitute those into the equation pi. And so we have 4 times x, because I want to find the point of intersection, minus 3 times y plus z equals 19. Let's distribute everything out. So we have 4 plus 16t plus 9t plus 2 plus t equals 19. What does that give me? 26t plus 6 equals 19. Subtracting 6 tells me that 26t is equal to 13. Dividing by 26 tells me that t is equal to 1/2. So let's just stop here for a second and think conceptually about what this means. This means that if I start at point P, so I'm going to go back up to my line equation. If I start here at point P and I move 1/2 of the normal vector, then I get to the plane. And so the distance between point P and the plane is 1/2 of the normal vector. So if I move another 1/2 of the normal vector, then I am at point Q. So let's use that to determine uh, the coordinates of point Q. So I'm going to take the answer I just got and double it. And so I'm going to use t equals 1. And I'm going to use that. So I know that the coordinates of point Q are going to be 1 plus 4, 0 minus 3, 2 plus 1. So that gives me 5, -3, and 3. And that should be the XYZ. I guess I shouldn't have written it as a column vector. So I'm going to write it just again as the point. 5, -3, and 3. So that's the coordinates of the point Q. It is on the other side of the plane, and it is equidistant from the plane because we just moved along the normal vector. And we moved 1/2 t, got us from point P to the plane. So another 1/2 t got us from the plane to point Q. Now we got to find the exact value of the distance PQ. And the exact value of the distance PQ is the magnitude of the normal vector, because there is one normal vector in between P and Q. And so we're just going to take the magnitude of the normal vector for -3 and 1. And so that's the square root of 16 plus 9 plus 1. And that gives me 26. So the magnitude is 26. And we are done. Not so bad.